thank you very much for the presentation, and also thanks to the organizers for the invitation and for organizing such a beautiful session. So I'll be talking about non-vanishing of cubical functions over function fields. So there will be a lot of number theory in my talk. Most of all the results that I will present are joint work with Chantal David and Alexandra Floria, but I'm going to spend some time introducing and motivating the subject before I get to the results. So I'm going to start with the Riemann zeta function that we can think of it as defined by this infinite sum, the sum of 1 over n to the s with n equals 1 to infinity. And this Dirichlet sum is conversion for the real part of s greater than 1. So in principle, s is a complex variable. And it can also be written as a product. This is called an Euler product. So it's a product over all the primes, where each factor is 1 minus 1 over p to the s to the minus 1. And this function has many properties and is famously connected to the distribution of prime numbers. So let me mention some of the properties. It can be analytically continued to the complex numbers with a pole at s equals 1. It satisfies a functional equation. And so one way of writing this is to take the Riemann zeta function and multiply by some other factors that are all well-known functions. Okay, so these are elementary, and then there is the gamma. And then this new function xi satisfies a xi of s is equal to xi of 1 minus s. And so this will, in the talk, we are going to talk often about functional equations, and we just say the functional equations that relate, say, s to 1 minus s. And there is also some fun fact that will come back much later, which is if you want to express what's 1 over the zeta function, actually you can also write it in a series that is very similar to the definition. But instead of having 1 over n to the s, you have the Moebius function, mu of n divided by n to the s. Okay, so the Moebius function is mu of n is 0 if n is not square free, and if n is square free, you just take minus 1 to the number of primes dividing n. So what is famous about the Riemann zeta function is to understand the zeros. Okay, so it's known actually from the functional equation. You can see that it has zeros at the negative even integers, but then also it could have zeros where the real part of s is between 0 and 1. So the functional equation famously connects what's happening to the left side of 0 in the complex plane with what's happening to the right side of 1. Okay, and the Riemann hypothesis predicts that actually, even though the non-trivial zeros could be anywhere here between 0 and 1, they should all be in the symmetry, in the symmetry axis. So the real part of s equals to 1/2. And this is an important question because from this one can deduce very precise statements about the distribution of prime numbers. It's also important for Batman. Okay. Now in this talk, we are going to talk about Dirichlet L functions. So a Dirichlet character is a multiplicative function defined, for example, you can think that it's defined in the integer mod d, okay? And it can be extended to all the integers by periodicity, and it will have the condition that is 0 for the integers that are not coprime to d. Okay, so that's a Dirichlet character mod d. And then actually if you have a character, a digit character mod D, you can view it as a character mod any multiple of D. So actually, given a character, you can think that you have like a family of characters. You can see mod D or mod any multiple of D. So the minimal, so there is, you can kind of try to get the optimal D. Okay, so is it the smallest modulo to which you can define the character? Okay, that is called the conductor of the character. Okay, and a character of conductor D, okay, that is sort of the D is the conductor, will be called a primitive character. It's like the first time the character appears is with D, modulo D, and then all the other times that the character appears is modulo multiples of D. So the smallest D is the conductor. So in this talk, I'm going to always talk about primitive characters with certain conductor. And the conductor is important because I will order the characters by conductor. I will think all the characters of conductor up to X. Okay, so once I have the characters, I can construct digit L functions. And so the digit L function is like the construction of the Riemann zeta function, but now instead of having 1 over n to ds, I have the character on n over n to ds. And so it has a very, in principle, this series again converges for the real part of S greater than 1. And it also has this expression that I called before the Euler product. So it's a product, or you can think of it as a product of factors over the primes. And it can be analytically continued to the complex plane. And it has a functional equation that relates S to 1 minus S. And if the character is not, so the character is a function taking values in the complex number. So if the character is non-real, you also have to conjugate it when you do the functional equation. So I'm not going to write the functional equation, but it's similar to the one I showed you for the Riemann zeta function. Now, a natural question to us is, so for the Riemann zeta function, we said that, okay, the Riemann zeta should have the zeros. Okay, the Riemann hypothesis says that the Riemann zeta function should have the zeros at real part of S equal 1/2. And in here, well, we could kind of ask the same question. And in fact, if you ask exactly the same question, that's called the generalized Riemann hypothesis. So assuming that the non-trivial zeros are in that line. But we are going to be more modest here, and we are going to just ask, okay, what happened at 1/2? Okay, so when you study the Riemann zeta function, you just have one function, but here you have a family of functions. So you have one for each digit character. So you could ask, okay, sometimes, maybe sometimes in 1/2 this gives you 0, sometimes it doesn't. And this type of question is associated to some sort of general philosophy in mathematics that has to do that the non-vanishing of L functions is either super trivial, like, the vanishing of L functions is either super trivial or it has some arithmetic meaning. So the non-vanishing should have some arithmetic meaning. And so, for example, the Beers and Sinerton-Dyer conjecture is about L functions associated, say, to elliptic curves. And they are having a 0 means that you have an elliptic curve of positive rank. So it's some deep meaning to have a 0 at the center of the critical line. So digit L functions don't have any arithmetic reason why they should vanish. And so the expectation is that they don't vanish. And this is what is called Choula's conjecture. And it was initially stated for quadratic characters, but then is expected to be true in general for any digit character. So in this talk, we're interested in studying non-vanishing, and in in a statistical way, in a sense that we want to count how often we have non-vanishing. And the method that we're going to use to study this is the method of moments. So the moments of diriged L functions are going to be given by a sum like this. So let me explain what the sum is. So the terms that I'm summing are fixed powers of L functions evaluated in 1/2. So I'm summing over different characters. Now, there are infinitely many characters. So I don't want to do an infinite sum. This is certainly non-convergent if I do an infinite sum. So I'm going to restrict to the characters that have conductor up to certain number that I'm going to call X. So I'm going to do the sum over all the characters that are primitive up to conductor, with conductor up to X. And so the star actually means primitive. Okay, so primitive, of course, makes sense. Otherwise, it's like I'm counting the same characters many times. Okay, because I will be counting for D and all the multiples of D that are less or equal than X. So I'm asking primitive so I don't overcount. Okay, so what's the relationship between this and non-vanishing? Okay, I can use moments to prove non-vanishing by an application of the Cauchy-Schwarz inequality. So if I start with the first moment, so K equals 1, and I apply Cauchy-Schwarz, okay, I'm going to get, so I imagine here that each term I'm going to multiply by 1. So for my Cauchy-Schwarz, I have the sum of A times B. So I'm going to take A to be the function and B to be 1. And so here I get the second moment. And here I get a 1 only when the term was non-zero. So I get a 1 only when the L function is different from 0. So if this sum that is written in a weird way is actually just counting the number of times, the number of characters for which the L function is different from 0. And then if I flip things to the other side, I get a lower bound for the number of characters for which the L function is different from 0 as a quotient of, this is a first moment square divided by the second moment. So if I understand well the first moment and the second moment, maybe I'm lucky and I can count, at least give a lower bound for the number of characters for which the L function is different from 0. So let me remind you that we expect all of the characters to work like that, but we are far from proving that. So at least we want to say that there's a positive proportion of characters for which the function is different from 0. Okay, so summarizing, basically what we want is that if the number of characters of conductor up to X is, say, some constant times X, then we would like to have a result saying that the number of times the L function is different from 0 in the same set is at least some constant times X. Okay, so here the constants don't matter so much. I mean, obviously B2 should be smaller than B1, otherwise we're in trouble. But I mean, we are happy just if we have some positive constant in both sides. And so that will give a positive proportion. So what is known about this topic? Okay, so actually random matrix theory predicts what the characters should be in the case of quadratic L functions. So this is for, sorry, what the moments should be in the case of quadratic L functions. So this is for quadratic characters. So it's given asymptotically as some constant depending on, so if this is the K moment. So this is some constant depending on K times X times some power of log of X. And so this is a conjecture, but it's actually known for K equals 1, K equals 2, K equals 3. For K equals 4 is known as assuming the generalized Riemann hypothesis. So assuming that is known. And then with these results, unfortunately, we don't have a positive proportion because if you look at if you look just at the conjecture, you have that x times a power of log, and this power of log grows as k grows. So basically, when you feed that in the Cauchy-Schwarz inequality, it will give you, say, with the first and second moment, it will give you x over log x with some constant, it doesn't matter. But this x over log x is not a positive proportion because the number of characters is like x. And so what happens is that your proportion of non-vanishing is 1 over log x. And when x goes to infinity, this goes to 0. So it doesn't really prove what we want. In fact, what we want has been proven with slightly different methods. So Soundararajan proved this for mollified moments, and mollified moments is what I'm going to explain later. And he got a non-vanishing proportion of 7 over 8. So as x goes to infinity, the proportion approaches 7 over 8, at least. And there is a better proportion with a different method that is called one-level density that I'm not going to discuss much, but also assuming the generalized Riemann hypothesis. Okay, so that was for the quadratic case. And then for cubic case, so working over Q, over the rationals, we can talk about cubic characters. I'm not going to define them in detail, but the idea is very similar to quadratic, to the Legendre symbol. So the idea is to take the number to the power of p minus 1 over 3, like in the Legendre symbol, you take p minus 1 over 2. And this case is called non-Kummer because when you define when you define cubic characters, the values that the cubic character can take are third roots of unity. And the third roots of unity are not, well, except for 1, but the other 2 are not real numbers. So they are not part of Q. So somehow this changes the picture a bit. So if the third roots of unity are present in your base field, then you're going to get different results. So this is called non-Kummer because the third roots of unity are not present in the base field. And then for this case, only the first moment is known, and is known to be some constant times x. This result actually it fits what is conjectured in this case. So in this case, it's conjectured that the moments actually are all constant times x. So a constant that depends on k, on the moment that I'm computing, but it's always a constant times x. So in principle, in this case, if we could compute higher moments, we could get a positive proportion. But the knowledge in this area is really far from computing higher moments. There are only some bounds, and so using those bounds, there is some proportion that was got that Bayer and Young got, but it's not really a positive proportion, and it's not even really 1 over log of x, it's 1 over some power of x, so it's really bad. When x goes to infinity, it goes to 0 very quickly. There is the other case, like I said, if the third roots of unity are present in the field, this changes the picture a bit. And so if we take the extension of Q adjoint the third root of unity, this is called a Kummer case. And now we are not really technically working with Dirichlet characters, we're working with Hecke characters, but we can construct everything similarly using the arithmetic of Q adjoint the third root of unity. And in this direction, there is one result also with the first moment, but it's a little bit of a restricted result by Luo, because, okay, so this sum the terms under the sum are a bit technical, but basically what they are saying is that they're going to take the conductor to be square free. And actually, when you work with cubic characters, you want your conductor to be cubic free, but not square free. And somehow it's like for each prime, you get 2 characters because you have 2 non-trivial roots of unity. And it's like the author is like choosing one of them. So he's going over this sum with a restricted set of characters. So it's what we call a thin subset. And so what he gets actually cannot really be compared in the context of the previous results. And in fact, because in this case, the number of characters should be x log x. And here he gets x. But like I said, because he's going through, I mean, it's not even half of the characters. It's like for each factorization, for each prime factor, you are choosing 1 instead of 2. So it's a much restricted sum. And this is all that is known over number fields. Now, finally, I'm going to talk about function fields and working over FQ. So what we need to keep in mind here when working over FQT is that we can do arithmetic over this field in a very similar way as we can do arithmetic over the rationals. Okay, so my base field is going to be FQ adjoint T, the rational functions in T. Q is a power of odd prime. Okay. So the corresponding thing to the ring of integers in this case are the polynomials. And we also have factorization in irreducible polynomials. So in the same way that we often work with just positive primes, we're going to work with monic irreducible polynomials. Okay, so this is going to be like the generators of my prime ideals. And we can also talk about norm. And we can define the norm of the number of elements in the quotient by the ideal generated by f, my polynomial. And this actually gives q to the degree of f. So instead of just being the absolute value of n, now we have q to the degree of f. And then with that, we can define the Riemann zeta function in this context as the sum over all the monic polynomials of 1 over the norm of f to ds. So in the same way that before I have 1 over n to ds. And what is nice is that in this side of the world, the Riemann hypothesis is actually true. And I actually have the proof here. So if we write the Riemann zeta function like this, okay, so like what we wrote before, okay, so just instead of having numbers again, I have the absolute value of the polynomial. Then if we want to do this sum, we could do this sum. Okay, we replace the absolute value of f by q to the degree of f, so we get q to the s degree of f. And then we can do the sum by degree. And so because all the polynomials that have the same degree will give the same term here. Okay, so we just need to count how many polynomials have the same degree. Okay, so if we are thinking about polynomial of degree d, okay, they have to be monic. So there are actually q to the d possibilities for the other coefficients. And so like that, you can actually write the sum just going over the degrees and counting that there are q to the d polynomials with degree d. And then, I mean, just power series, okay? So the final value for the Riemann zeta function is 1, the final sum is 1 over 1 minus q to the 1 minus s. And so it has a particular nice expression, and and it doesn't have zeros really. I mean, it just have pole at s equals 1, clearly, because that's when q to the 1 minus s is 1. But it doesn't have zero. So the Riemann hypothesis is true. Now, what I meant when the Riemann hypothesis is true is not just for the Riemann zeta function, but also for the Dirichlet functions. And so we want to talk about Dirichlet functions in this context. So again, a Dirichlet character now is going to be defined over the polynomials modulo some fixed, if you want, some fixed polynomial d of x. And again, it's a multiplicative function that can be extended to all the polynomials by periodicity, and also with the condition that chi of a is 0 when a is not coprime to d. So it's a very similar situation. And then we can build the Dirichlet function as before, okay? And we could do the same trick that we did for the Riemann zeta function, okay, separating by degree. And when we do that, okay, so before we have q to the d, but now we have a sum of character over all the polynomials of fixed degree n. And what happens is if n is big, I mean, bigger than the degree of d, this is what is called a whole character sum, and it gives you 0. So if the character is non-trivial, it gives you 0. Think about like summing all the roots of unity. So all the powers of a fixed root of unity, if you want. Okay, so then what happens is this term becomes 0 for starting at a certain point. So this sum actually is the finite sum. We can be more precise about it, and there are very deep reasons for this. So I just want to mention a bit the case of quadratic characters. So quadratic characters, again, are defined like the Legendre symbol. I'm not going into the details of that, but basically, this is what I have in mind, the Legendre symbol. And sometimes I will prescribe certain conditions on Q. In this case, I'm asking that Q is congruent to 1 mod 4, and this is just to write things a little bit more clearly. When Q is congruent to 1 mod 4, what we have is that quadratic reciprocity becomes trivial. And so writing this is the same as writing, oh, okay, it's gone, but it's the same as changing the order of F and D. And in this case, we have a geometric interpretation for the Dirichlet function. So if we consider the curve y squared equals dx, okay, and here is the same d, then we can consider the Weil zeta function associated to this. And if the degree of d is odd, and I'm going to write it as 2g plus 1, then the Weil zeta function will be written in this way. So, well, it's always a rational function, but when the degree is 2g plus 1, we can write it as some L divided by 1 minus u, 1 minus qu. And this L is actually the same as the Dirichlet function that I showed you before. Now, okay, so the variable is completely different. I should say this, you have to make a change of variables. Sorry, this goes away. Let me write it in more precise. Okay, so if you do this change of variable, you actually get the same, you get the same Dirichlet function that I showed you before. And so actually then you can use the Weil conjecture to deduce things about it. And so the Weil conjecture will say more precisely that this is a polynomial of degree g. There is a functional equation relating u and 1 over qu, but this is the same as s and 1 minus s. So it's the same functional equation that is always showing up with us. And also the Riemann hypothesis holds in general. Now, in this case, just quickly, I wanted to mention, so for the quadratic characters, the moments, again, there's a conjecture about the moments. So before we have x log x, and we have different powers of log x. Now we have q to the 2g plus 1, which is like an x. And then the 2g plus 1 is like log of x. So if you take log of this, okay, so suppose that q is actually the exponential if you want, or you take log with the basis of q. So if you take log of that, you get 2g plus 1. So the conjecture is essentially the same. And in this case, this is known for k equals 1, 2, 3, 4. And respect to non-vanishing, there are some results actually not using moments, again, using what I mentioned before, the one level density, and it's a very nice result with 94% of non-vanishing at least. There is also some vanishing, okay, which is this star ring. So far I've been like, oh, no vanishing, no vanishing, no vanishing, but actually there is some vanishing, a very small vanishing. So this is like x to the 1/3. So it's actually a proportion of vanishing that goes to 0 as x goes to infinity, but still is some, so there is some vanishing. So we cannot expect to have a result like a very theoretical result saying, if you give me an L function like this, there will be non-vanishing at 1/2. That we cannot expect. There are some functions for which this the central value vanishes, but the proportion of them goes to 0 as x goes to infinity. And then last week, actually, there was an announcement for that in some case, some people prove non-vanishing for 100%. So 100% doesn't mean all the functions. It means that when x goes to infinity, this approaches, you know, x. The number of characters, but it doesn't mean that you could not have like in between some functions where there is some vanishing. So these two results don't contradict each other. Let me just say that. However, I don't have any much details about the last result, but it doesn't use moments. This is for quadratic, so you see that there are many different ways of seeing this non-vanishing for quadratic. Now I want to talk about cubic characters, which is the main topic for me. So in cubic characters, we also have, remember that I mentioned the Kumar case and the non-Kumar case. The Kumar case had to do with having the third roots of unity present in the base field, and the non-Kumar case is when they are not. So if Q is congruent to 1 mod 6, then the cubic root of unity are present in my base field. And then, so this is the Kumar case. This is like Q adjoint the third roots of unity. So in that case, we can build the cubic character again using this trick of a minus 1/3. But now, because we are in function fields, instead of taking just the polynomial, we take the norm. Okay, so we take the norm of p minus 1/3, and because the third roots of unity are present, we can always do that. Okay, and we had to make some correspondence between the third roots of unity in the finite field and the third roots of unity in the complex. Okay, so that this becomes a character that goes to the complex. And so we define this modulo p for any monic irreducible polynomial p. And then if this is for p not dividing f, and then if p divides f, we extend it to 0. And then if we want to extend it modulo just anything, not just a prime, or not just an irreducible polynomial, we can just use Jacobi symbols. So this is very analogous to the construction that one does with quadratic characters. And then in this case, there is also a geometric interpretation. So for the quadratic character, we have y squared equals d of x or d of t. In this case, we can relate it to some cubic curve. Well, I shouldn't say cubic curve because the right-hand side has much bigger degree, but a cubic cover. So y cube equals some polynomial, and now my polynomial is cube free. Okay, so we're going to write it as something that is square free times a square of something that is square free. And in this context, there is also some relation with the Weil zeta function that I'm not going to discuss in detail, but just let me say there is some relation with the Weil zeta function. And the genus associated to this curve is going to be, so before, for the quadratic case, the degree of D was 2G plus 1. So the genus of the curve was growing together with the degree of D. In this case, the relationship is much more complicated because the genus is given by the sum of the degree of the first polynomial and the degree of the second. But I have a square here. So this is not the total degree. This is just, forget about the square. So the relationship is a bit more complicated. But then also we can look at the moments, summing over all the characters with some fixed genus. And so here's our result. So here I wrote Q congruent to 1 mod 3, but it's all. So this is 1 mod 6. So if we sum overall the cubic L functions in the central value in 1/2 with fixed genus, then we get an expression that is some constant times G times Q to the G, and some constant times Q to the G, and then some error term. And so this number is comparable to the total number of characters. So this is good news. Okay, so we're getting the first moment and we're getting everything. So this is better in a sense that the result that I showed you earlier for number fields, because the result I showed you earlier was over some, there was a restriction on the character, but this is taking all the characters. Now this is joint work with Chantal David and Alexandra Floria. So I thought about putting the pictures here. And then we also look at the non-Kummer case. So the non-Kummer case is when the third roots of unity are not present in the base field. So here we're going to ask that Q is congruent to 2 mod 3. So because Q is congruent to 2 mod 3, you don't have the third roots of unity in FQ. But we can still build cubic characters. It's just it's a little bit more complicated. But and we get that the first moment is given by some constant times Q to the G. The previous result with Kummer was like X log X, and this result is like just X. Okay, and this is okay because the total number of characters is also like a constant times X, so constant times Q to the G. So this is great for first moment, but then when one tries to evaluate second moments, is really hard. There is no estimate for what the second moment is, except for conjectures, and but they are bounds, and so you can always bound it using something that's called the Lindelof bound. That is a consequence of the Riemann hypothesis, which in this case is actually true because we know that the Riemann hypothesis is true. But those bounds, so it doesn't bound the second moment really well. So we get a non-vanishing, but it's not a positive proportion because we are dividing by G. It's like we are dividing by log of X. There are some slightly better results using other methods for not vanishing, using some algebraic geometry, like in some cases there is X over square root of log X. And also the same people that prove, so Wanlin Li, who proved that there was some vanishing in the quadratic case, she also proved that it's some non-trivial vanishing in this case. But again, it's not a positive proportion, so we're still not in contradiction with what we want to prove. let me just say that all this method that I keep mentioning from time to time, the one level density, actually doesn't work in this case at all. So it's not like I'm missing something because I refuse to use a method that I don't like or something like that. I mean, it really doesn't give a good result. It does give a good result if we restrict the characters to this special family that the theme family that I mentioned before for Luo's work. So in that case, it gives a positive proportion actually. So it's very nice, but we cannot use it for the whole family. Okay, so the main result I wanted to present today is the non-vanishing for the non-Kummer case. So Q congruent to 2 mod 3. And the result is that the number of characters for which the L function at the central value is different from 0 is bounded below by some concrete constant times Q to the G. And so this is a very concrete constant. And this is a real inequality. So often I have this, which means up to a constant, but this is a very concrete thing, and I'll give you the constant later. And the arguments in this proof should also work for the Kummer family. We didn't complete the details, but the fact that it's non-Kummer doesn't really change. It's just a little bit technically simpler. Okay, so I want to tell you a little bit about the main idea behind the proof. So I mentioned several times already that for the first moment, we expect to have that the main term is a constant times x. Okay, so because this is a non-Kummer case, so it's a constant times x or constant times q to the g. And I also said that there are some bounds for the second moment that are not great, but we can still have them. And so we have some bounds like constant times g times q to the g. Okay, so if we didn't have this g here, we will win. But unfortunately, we have this g, and so when we do Cauchy-Schwarz, okay, with the trick I showed you earlier, okay, so we get a constant times q to the g over g, and this is bad. Let me remind you, because the size of the family is a constant times q to the g. So we are unhappy because we have this g and we have this g here. So that's the problem. That's the main difficulty. Now, here comes an idea. It's called the idea of modified moments. And so it goes back to Selber, studying the Riemann zeta function, but also it came back with Sandra Rashan, who studied the Riemann zeta function, also Dirichlet functions over number fields. So the idea is to create a function, m of chi, that behaves like the inverse of L of 1/2 chi. So for each chi, you have this L of 1/2 chi. And for those that are different from 0, okay, you can consider the inverse, okay? And you build a function that looks a lot like that. So suppose that we can build this. Then when we do the first moment, okay, so instead of computing the moments, we're going to multiply this L by this M. So all the time it's like now we attach this M to L. So now when you multiply like that, it's like each term that was non-zero to begin with now becomes something very close to 1. And so your first moment still has the same shape, x times, you know, a constant times x, a constant times q to the g, because that's the number of terms you have in the sum. So even if you have a bunch of ones, you will have some result like that. But then the second moment, if this is very close to 1, then when you do this sum, it's like you're counting the number of terms. So you also should have a constant times q to the g. Okay, so before we have a constant times g times q to the g. But now, if we find a smart enough function like this, we have a constant times q to the g. Okay, and so when we do Cauchy-Schwarz, then that's how we should get the constant. Okay, so the moral of this is that classical moments, no, but modified moments, may give some good result. Okay, so I have some details about the proof, but it's kind of sketch. So for the first moment, let me just say that evaluating the modified moment is not very different than evaluating the regular moment. So when you evaluate the modified moment, you get multiplied by a character in each term. Okay, so it gets multiplied by this m, but after you get out all the extra things, you get just a character. And then it uses the same methods as evaluating the first moment. So the first results that I told you about. So the first method is using something that's called the approximate functional equation. And it has to do with, you know how I mentioned that there is a functional equation associated to L, but this is a functional equation that you kind of flip, you know, the functional equation flips S to 1 minus S, but you kind of flip part of the L function, but not the whole thing. And so the parts that are not flip, like they stay with S, are called principal, and the parts that are flip are called dual. And then you get that the main term actually comes from summing over cubes on the principal part. And so this can be evaluated with something called the Perron formula, which is, in this context, is a fancy way to call Cauchy's theorem. In number fields, this is actually a very delicate theorem, but in this context is rather easy. And then there are terms that are coming from non-cubes, and those can be bounded by this Lindelof bound that I mentioned before, which is related to the Riemann hypothesis, which in function fields is true. And then for the dual terms, those are the more complicated to evaluate, and they use what are called cubic Gauss sums, and cubic Gauss sums are very difficult to evaluate. So the part that is hard in this result has to do with working with these cubic Gauss sums. So that's for the first moment. The second moment, okay, so for the second moment, we're not actually evaluating the second moment. We're just bounded it. And the method uses, depends on works that were done before to bound moments of the Riemann zeta function and other moments. So works of Soundararajan, Harper, and Lester and Radziwill. Maybe I'm gonna go quickly over that. Okay, so the first step has to do with, so we want to bound L, but instead of bounding L, we bound log of L. And we write like a finite sum plus some terms that we can somehow control. So the finite sum, the more terms we put in the finite sum, the better the other terms are. But of course, there is some negotiation there. So we do that, and then we want to bound L, so we actually take the exponential. So it's like going back and forth. So we take the log, then the exponential. So when you take the exponential, even though you have a finite sum here, you don't have a finite sum anymore. And so then you have to bound the exponential with a finite sum. So it looks like a big, big detour. And there are some conditions on that. And so it ends up being a question of whether what you have inside is large or small. But maybe let me just comment on that. So that thing that you have inside the exponential, when you take powers, you are going to get a sum that has a character, has the norm of f to the 1/2, and then an extra function that is a multiplicative function. And so this looks a lot like the L function, that there is a L function in 1/2. Okay, but it's a finite sum, otherwise it doesn't converge. And so one can use this to define this modifier that I mentioned before. And the way we define it is essentially taking the same sum, but putting a power of -1 here. And putting this power of -1 is like putting the Moebius function that I mentioned in the very first slide when I said the inverse of the Riemann zeta function is by just plugging the Moebius function there. Here is like we plug the Moebius function. It's just we plug a different like a relative of the Moebius function that is completely multiplicative, but it's essentially that. So that's how we define the inverse. So we take this term, instead of the L function, we actually take this term, and the modifier is like the inverse of that term. And then there is some problem, like if you try to estimate, actually you still get some log things. And so we have to cut some interval in pieces. Okay, so this is quite technical. But the idea is that this is an interval of degrees. So like how many, I'm gonna take all the polynomials, reducible polynomials of degree up to something. And then if I take the whole integral, I get a bad bound. I get q to a g, but with some log of g. And I don't want log of g. G goes to infinity. I don't want that. I want just q to the g. And so if we cut the interval in two, then we get, instead of log of g, we get log of g. And log of g is better than log of g because it grows more slowly. And so the idea is that you cut the interval more and more and more. And each time you cut the integral, you get log. Okay. And you cut the integral into something that goes to infinity number of intervals. And this, in the end, morally, you put so many logs there, then it becomes constant. And it's, when I say morally, it sounds like, oh, it doesn't grow fast. No, but it really becomes constant. Okay, so this goes away and you get q to the g. So that's how you get. Now, the problem is this process, there is a price to pay with the constant. So when you do this process, you generate a constant of exponential of something that depends on k. And so finally, what happens is that, you know how I said there was a C positive constant, very concrete? Yes, it is very concrete, but it's very, 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 very tiny. Okay. So what our result is, the full result is that the proportion, we can guarantee that the proportion of cubic characters for which the central value of the L function is different from 0 is at least 0.47 times the exponential of minus the exponential of 182. And I can guarantee that if you plug this in a computer, it will tell you 0, but it's a positive number. So it's really tiny. Okay, so thanks. Muchas gracias por su atención. Muito obrigada. Thanks for your attention. Merci beaucoup.
Right. Thank you very much.